Well, greetings. We're going to go ahead and start the webinar here. Hopefully everybody is here for Dr. Reid Castrodale's presentation on the primer on lightweight concrete for bridges. You can see there on screen is Dr. Castrodale's contact information if you need that, and I'll be dropping it in the chat here in just a little bit, so you will have opportunity. If you want to contact Dr. Castrodale after the presentation, you'll be able to. I will be making the slides will be available sometime after the presentation, along with a link to the recording. You'll find that on the ASBI website at the place where you registered. Also, Wade Bonzen, our chair of our ASBI Construction Practices Work Group, will be joining us today to do our Q&A. And I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute, so I'd like to welcome you for attending today. We'll do a few announcements real quick. Our April webinar, Ben Soul with Sistra IBT will be leading that, talk about incremental launching for concrete segmental bridges. I know this is a topic that really doesn't get a whole lot of attention in the US, and I personally kind of wonder why, and I think it's a good opportunity for you all to learn a little more about this construction technique and the potential applications. American Segmental Bridge Institute is also hosting a grouting certification training April 24th in person in Austin at the Commons Center of the J.J. Pickle Research Campus. That registration is open on the ASBI website. This isn't just for segmental. That is to say, if you are involved in a post-tension structure with grouted post-tensioning, this training is really essential, and so I'd encourage you to attend the April 24th training if you're at all available. Also, just a little thing to put on your calendar, ASBI's annual convention and committee meetings are November 5th through 8th at the Westin La Paloma in Tucson, Arizona. Registration for that will also be open soon on the ASBI website. So at this point, just encourage you to put that as a little note on your calendar to block out some time. We do have a new ASBI publication that's available on the website for free download. It's a publication called our Durability Survey of Segmental Concrete Bridges. This is an update, been 10 years since the last time we published a durability survey, and it's just an update on how our segmental bridges performing across the country, and the answer is they're actually performing very well. And so you'll find some information in that publication about more detail on how they're performing. So some quick webinar instructions. If you lose your connection today, don't freak out. You can log back in with the link you were provided. And of course, you will miss content while you're away. It's just like walking out into the hallway during a live in-person presentation. We will issue certificates of attendance for those who meet their minimum requirements in the session. Again, we're giving 1 hour PDHs, so as close to 1 hour as you can be, the better. If you'll give us a week to get your attendance certificate to you by email, we appreciate that. We don't anticipate that it'll be that long, but we don't use a manual system. Our RCEP requires us to manually go in and verify attendance. So with that, again, wait about a week and you'll be then getting your certificate of attendance. And we will do question and answer at the end of the presentation today. And this gives you sort of an idea of how the Q&A will work. It's in writing since we don't have the ability to do audio questions. You should have on your dialogue a little questions box. Little pull down. You can hit that, type in your question and hit enter. And you can do that at any time during the presentation. You don't need to wait until the very end if you have a question on the fly. And certainly our presenter will be able to go back if you need to reference a particular slide number. If you're on a mobile device, you should have a little question mark where you can click to do a question, same format as what we had on the desktop version. This is our obligatory slide about ASBI meeting the RCEP requirements for continuing education. That's through which we're going to be issuing your continuing education certificate. So today's speaker is Dr. Reid Castrodale with Castrodale Engineering. He's here today as an expert in his background in lightweight concrete, and specifically, he's the primary author of the primer on lightweight concrete for bridges that was recently published by the Federal Highway Administration, so he's going to be talking about today. He's also a consultant to the Expanded Shale, Clay, and Slate Institute, ESCSI. We think of them as the lightweight guys. That's the primary industry group that promotes and is the keeper of knowledge on lightweight concrete. He's worked with a number of engineering programs as program manager for bridges at the Portland Cement Association. He's a PCI fellow, a very proud graduate of Georgia Tech, and also holds a master's degree and doctorate from the University of Texas at Austin. So, and his research was primarily in pre-stressed concrete bridges. So Reid comes to us today highly qualified to cover this topic. In fact, there's probably not anybody in the country more qualified than Reid. So with that, I'm going to turn it over to Reid as our presenter. And the floor is yours, Reid.
Very good there. Thank you for the introduction, Greg. Glad to be here. And let me click one more time and we'll get hopefully something showing up. There we go.
Yep, we got it.
All right. Well, thank you very much. Get set here and we're ready to roll. I'm excited about this opportunity to introduce the new resource, the Lightweight Concrete Bridge Design Primer. And by taking this opportunity to introduce it, I'll also be introducing you all to lightweight concrete for bridges. The primer was developed by FHWA through a contract with WSP. And I'd just like to acknowledge the contributions of Andy Foden, who's now with HNTB, but he was the project manager for WSP and did contribute a good bit to the direction and review of the primer. Just thought I'd mention that the bridge in the photo here on the first slide is in Eastern Virginia, and it's an example of a bridge constructed fairly recently with lightweight concrete. It has lightweight concrete girders and a lightweight concrete deck for the two main units, which have spans of 200, 240, 240, 200. To get those spans, the girders were spliced and post-tensioned. Right now, unfortunately, the bridge has some issues with grouting of the tendons, but the lightweight concrete is performing well. And I'll show you a number of other project examples taken from the primer later in the presentation. And I thought I'd give you one other heads up that I have hidden a few slides in the presentation. So there are a couple of times where the numbering of the slides may jump. Just thought I'd make you aware of that. Those hidden slides will be provided in the presentation that's posted when we get to the end of the presentation. And here is a disclaimer from Federal Highways. The primer was prepared for and it was reviewed by Federal Highways. The presentation's also been reviewed by Federal Highways. And really, this disclaimer is just indicating that the presentation is for information only and doesn't present binding requirements. And in a few cases, you'll see some notices in the presentation where some items are accompanied by a legal reference, such as the LRFD bridge design specs from time to time. So at any rate, you'll see some things that we're not used to seeing, but that's coming from the Federal Highways requirements these days. So let's get into it here. Structural lightweight aggregate has been manufactured commercially in the United States since 1920. So this is not a new material. You know, lots of people feel like lightweight concrete is a new material, but it certainly isn't. It was immediately used after it was introduced to produce structural lightweight concrete. And of course, the main benefit was its reduced density. But it was also found to be very durable. And we'll talk more about this, the San Francisco-Oakland Bay Bridge, shown in the photograph here. It does have lightweight concrete in the upper deck. In fact, it's all lightweight concrete, meaning it's about 95 pounds a cubic foot. And that was constructed in 1936, and I do believe that's still in service today. So let's talk a little bit about lightweight aggregate. It's a manufactured product. So this is not something like lava rocks that you might have in your grill outside, where they just dig it out of the ground and crunch it up, and that's what you get. In this case, what we're talking about is a raw material that's either shale, clay, or slate. You may have to blast it and get it out for the harder materials, but clay, they can just dig it up. So you use those as the raw materials, and then we heat them in a kiln. You can see the rotary kilns indicated by the arrows there. There are a couple of them at each side. Those kilns have the raw materials coming in from the top end, and it rolls down to the bottom. They're over 200 or 2,000 degrees Fahrenheit down at the low end where the flame is. So the material's getting heated up. It softens, doesn't melt, but it softens, and gas bubbles form in that material as it's softened, and then the gas bubbles remain after cooling. And you can see them here. It's a porous surface that you can see on the aggregate particles. The clinker is then typically crushed and screened. So that's how we get our lightweight aggregate. Lightweight aggregate was developed back in 100 years ago, and the process was patented. And then in the 1950s, that patent expired. And at that time, the use of lightweight concrete and lightweight aggregate increased rapidly as other manufacturers came in, and the rapid growth continued well into the 70s, at which point we had an oil crisis. And with the heating that was required for the aggregate to be manufactured, that meant that the price went up on what was being used, either oil or coal. And then the Environmental Protection Agency also began working in those days, and pollution controls were then being required to be placed on the kilns, and that increased production costs. So things changed markedly in the 70s, and there was a significant contraction in the market. About half of the deliveries went away, and as a result, the industry production was reduced, promotion was reduced, and then it became sort of constant at that lower level, and then we really didn't have much production or of promotion of the material after that point. Prior to that time, they had a newsletter and a lot of things where a lot of information was going out about lightweight concrete. So over the years since then, Federal Highways a couple of times has felt that there was promise in using lightweight concrete for bridges. And one of the strategies that they had to come up with some guidance, some information on lightweight concrete and how we could use it for bridges was to come up with a lightweight bridge design primer. That's what you see pictured here on the right side of the slide. The primer was published in November of 2021. That's the date that's on the cover, but it really became available more or less in the middle of 2022. It's available for download. You see a link here. There's going to be a link that's going to be placed in the chat at the end of the presentation, so you can grab it off of the chat and use it if you want to get a copy of the document. So it's a bit longer than what you might think of for a primer. It's about 133 numbered pages, but there was just too much good information. I've been collecting information about lightweight concrete for a good while, and I wanted to be able to share it, and so I put more in here than normally we'd have, but hopefully it will be of value to you and others over the years. This is the table of contents for the primer. I'll go into a little bit of detail in chapter 1, the introduction, then probably about a third of the seminar or webinar is going to be on chapter 2 regarding the properties of lightweight aggregate and of lightweight concrete. Then after that, I'll do some pretty quick introductions to chapters 3 through 6 and spend a little bit more time on chapter 7, where I'll introduce a few of the bridge projects for which lightweight concrete has been used successfully. I won't go into chapter 8 today. Normally I wouldn't anyway, because it's references, but there are 160 of them, over 160, and those are provided to give you more information to supplement the primer. And you can chase those down to get more information about the projects or material properties or whatever you're interested in. So I'd encourage you to use those. So now we'll jump into the introduction. And what we'll talk about here, we've already talked a little bit about lightweight aggregate, how it's made. But as far as lightweight concrete, this is the definition that comes from the ASBI LRFD. So lightweight concrete is simply a concrete that contains lightweight aggregate, and it conforms to the ASBI spec, and it has an equilibrium density that's not greater than 135 pounds a cubic foot. And then it gives you the specs that you use to compute or determine the equilibrium density. The equilibrium density is defined in ASTM C567 roughly as the density of structural lightweight concrete after exposure to a relative humidity of 50% and a temperature of 23 degrees C for a period of time sufficient to reach constant mass. So it's essentially a dry density of the lightweight concrete. What goes on here is that lightweight concrete is pre-wetted, the aggregate rather, is pre-wetted before it's batched. Therefore, it has some extra moisture in it, and that moisture can get away. Well, that moisture weighs something. So as that moisture leaves the concrete, if it's not bound in the cement, then you're going to get a reduction in the density of the concrete. So that's why we are talking about an equilibrium density. We used to talk about an air dry density for lightweight concrete, but that's not defined anymore in any of the test methods. So we shouldn't be using the term air dry density, but rather should be using the term equilibrium density. That's also discussed probably back in chapter 6, where it goes into the specifications. You may also note that the terms density and unit weight are used somewhat interchangeably, both in the primer, but also in the LRFD specs. It's not quite technically right, but it seems to work. So just want to reemphasize that lightweight concrete's not a new material. It's been addressed in the ASBI design specs since at least 1969. And then there was another study funded by FHWA and performed by T.Y. Lin International. It was published back in 1985. And here you can see a quote from that report that even back in 1985, there was enough information available, and lightweight concrete had been successfully used, and therefore it's a suitable construction material for bridges. So that's important, and again emphasizes that this is not a new material. So moving on, in the topics that are included in chapter 1, there's a list of benefits for lightweight concrete. And here we start out by taking a look at structural benefits, and those are items that are related to design efficiency for the superstructure, but also for the supporting elements. And here you can see some of the examples. You can extend the span ranges, wider girder spacings, shallower girders, all these sorts of things. Oftentimes, making a lightweight deck will give you increased spans more so than simply using a lightweight girder. Also, we have improved efficiency because of reduced design loads on the bearings and substructures, foundations, and all that sort of thing. And then there are the benefits of moving precast elements, that if they are lighter, it is a nicer thing to do. So that's another benefit for handling, hauling, and erection. But then there's something that's sort of a surprise to many engineers, and that is that durability of lightweight concrete is actually enhanced over normal weight concrete. Everything else being pretty much the same. Doesn't seem to make sense that if you're taking a rock with holes in it and you're putting it into your concrete, that it's going to be more durable than when you use a hard rock piece of aggregate in your concrete. There are a number of factors that enter in there. I can't develop that all. That's a very interesting topic, but one of the things is that the lightweight aggregate is typically pre-wetted before we put it into the concrete, and that helps with pumping it and other things. But it also helps with durability because it reduces shrinkage. It therefore reduces cracking, and it also reduces permeability because down on the micro scale, there's less cracking around the aggregate particles that you might see in a normal weight mix. Similarly, the aggregate is less stiff because it has all those holes in it. And therefore, since it's less stiff, you end up with less micro cracking. And when you have less micro cracking around the aggregates, you have lower permeability. We have a lower modulus of elasticity that can reduce cracking due to restrained shrinkage. And then finally, lower coefficient of thermal expansion also reduces cracking, and I'll get into that a little bit more in a minute. And it's especially if you combine the lower modulus and the lower coefficient of thermal expansion, which is something that happens when you're looking at, for example, a bridge deck cooling off after it's begun to set. That can have a significant reduction in the cracking potential because of restrained thermal and shrinkage strains. There are, however, perceived disadvantages of lightweight concrete, and that's probably why we haven't seen its lightweight concrete being used for bridges much more than they are now. There is the increased cost of lightweight aggregate. You're looking at an aggregate that's dug out of the ground like other aggregate, but then it's fired, and the number of sites where lightweight aggregate is produced is somewhat limited. So there's oftentimes a significant transportation cost involved in getting the lightweight aggregate to wherever you're wanting to make the concrete. People oftentimes think about reduced durability because you've got an aggregate with holes. Surely it can't be as durable. And then you see others here, reduced capacity, or probably it must have a reduced strength. That's not true. And, you know, is it available? And then many contractors are not familiar with lightweight concrete. However, the fact that we've had many successful projects means that the increased cost is not insurmountable, and other concerns, those listed there, can oftentimes be addressed either in design or they are simply misconceptions. For example, the reduced durability. I'll give you 3 quick examples of projects on which there's been an effective use for lightweight concrete. One's, again, the San Francisco-Oakland Bay Bridge, another a bridge in Washington State, and finally a bridge in Norway. The San Francisco-Oakland Bay Bridge, the suspension spans that you see in the photograph there, it was built in 1936. It has an upper deck that was made using what's called all lightweight concrete, which means all of the aggregate in the concrete is lightweight. That was specified at a 95 pounds per cubic foot air dried unit weight back at the time. There's an article out there by a guy that was involved in the design of this, and he says that using lightweight in that bridge deck saved $3 million out of the original $40 million total cost. That's 7.5%. So it's a significant cost savings for the use of lightweight concrete there. Then a number of years later, in 1958, the lower deck, which had been for rail and trucks, was reconfigured for the same traffic loads as the upper deck. So it was installed again using all lightweight concrete. and both decks are still in service. Now, both of them have had wearing surfaces on them, but it's pretty amazing that those decks are still in place today. Another bridge is the I-5 bridge over the Skagit River near Mount Vernon, Washington, and there was an emergency replacement a number of years back when one of the truss spans got impacted by an overheight load, and it brought down a truss span. The DOT called for RFP, or put out an RFP to get it replaced, and said that the total weight of the replacement span, if held below 195 tons, would avoid any analysis and retrofit of the piers, which is a significant item. So one of the teams that proposed the use of using sand lightweight concrete for precast deck girders. We'll talk about sand lightweight in a minute, but it's not all the way down at all lightweight, but it's a little bit more than that. The coarse aggregates lightweight. So these were the first lightweight concrete girders that had been made in Washington State for the DOT. The design compressive strength of those girders was 9 KSI at 123 pounds a cubic foot. The actual design strength, if you went through all the ACI statistics, looking at cylinder breaks for actually a number of projects, it comes in at 10.6 KSI. So that indicates that you can get a high strength concrete, a design high strength concrete out of lightweight concrete. These girders are 162 feet long. You can see the other details there, but this is a significant project that introduced lightweight concrete up there in Washington State. Then there's one other bridge that I wanted to talk about at this point, and that's the Rugsund Bridge in Norway. It uses lightweight concrete for the center span, a part of the center span, for alternate design. So there was designed in normal weight concrete. There was a peer review process that said you ought to really take a look at lightweight concrete. When they looked at lightweight concrete for that portion of the center span, they were able to increase the length of the main span by 10%. But it still used the same quantity of post-tensioning, even with that longer span. So that moved the foundations into shallower water. This is a bridge over a fjord that gets deep very quickly. So they saved a bunch of money on the foundations. And you can see that it did some other things there as well. So when that went to bid, the lightweight concrete design was 15% less than the normal weight bid. And since pumping was an issue for the contractor, he really wanted to pump lightweight, they actually had to bring the lightweight aggregate in from the United States to allow that pumping. But it was still cheaper to bring the lightweight aggregate all the way from the US into Norway than it was to build the original design with the shorter spans, deeper foundations, and all that. This is an excellent example of where you need to take a look at the project impact, not just to look at the cost of the difference in aggregate. So let's move into chapter 2 now and get to the discussion of lightweight aggregate and lightweight concrete properties. We'll begin by looking at the lightweight aggregate properties, and then move on to taking a look at lightweight concrete properties. And finally, we'll have a brief discussion on internal curing, which is where we're modifying a normal weight mix by replacing a fraction of the fine aggregate in the mixture with pre-wetted lightweight. And what that does is those aggregate particles have water absorbed in them. So as the concrete sets, it pulls the water out of that aggregate and cures the concrete from within, which is a very effective process. So we have a number of different kinds of aggregate. You can see a picture here. It's from an NCHRP study, but it's showing 6 different kinds of aggregate. They're the different sources that you see, the shale, clay, and slate. So the properties vary a bit depending on source and processing, just like aggregate, normal weight aggregate varies from source to source. The lightweight aggregate is typically crushed, but it can be uncrushed. You see that in the bottom right photograph, that this is an uncrushed, pelletized type aggregate, while this is a crushed aggregate on the right side of that photograph. The properties of lightweight aggregate, that is the gradation for coarse lightweight, are given in AASHTO M195. This is a chunk out of the table. It's not the whole table, but it's a piece of it that's showing the coarse aggregate gradations. We don't have gradations that are 57, 67s, whatever, that kind of thing. It's just 3/4 inch, 1/2 inch, and 3/8 inch, based on the maximum aggregate size. So there are specifications, just like for normal weight, there are specifications that specify the gradation and other properties for the lightweight aggregate. There is also a gradation available for fine aggregate. Lightweight aggregate, because it's an expanded rock with pores, it has an increased absorption compared to normal weight aggregate. So that absorption may range from 5% to more than 25%, as it says here. So it's typically higher, a good bit higher than normal weight aggregate. Again, it depends on the source and all. And one thing that we should call a caution here is that absorption alone shouldn't be the only criteria that's considered to determine acceptable performance for lightweight aggregate. We need to look at the whole picture there. And in the past, some agencies may have also prohibited the use of lightweight aggregate that's been crushed. California used to have that in a spec, and that was to minimize absorption, but that was for the type of aggregate they had out there. If we're looking at nationally, that's not a necessary requirement, and may not even work for that one. But at any rate, it's not something we want to do. So those are some cautionary statements there. Absorption of lightweight fines are shown here in two figures. On the right figure, it shows the mechanics of the absorption are essentially the same. Let's go back to the left figure. It shows the range in absorptions. You see that the bottom line after 48 hours, 2 days being soaked, it's somewhere in the neighborhood of 6%, 7% absorption, while the top one here is up over 32% absorption. So there's a fair range. There is a middle ground here where most of the aggregate types are. But if you normalize them all by their 24-hour absorption, you see that they all pretty much have the same shape. So they are behaving quite similarly with respect to the rate at which they take up water and that sort of thing. Now, the absolute quantities are different, but the relative quantities are the same. This is a graphic that illustrates the condition of three aggregate gradations. This is theoretical, where you're taking a look at what's the solid portion of an aggregate, the pores, and then what of those pores can be filled with water when you reach that absorption that you might have seen in the preceding slide. So it varies, the absorption varies, but still, even though you have absorption that is essentially stabilized at this level, there are pores that are inside the aggregate that are not filled. So typically only 20 to 50% of the pore volume of an aggregate particle will be filled. What that tells you is that those pores are disconnected. They're bubbles that are totally surrounded by rock, and therefore water can't get to those pores. So we don't really reach a saturated condition. We don't call it that. Wetted, surface dry is what we like to use. So that's just something to be aware of, that the empty pores don't all fill up with water when you soak lightweight aggregate. What about the durability of lightweight aggregate? Here's some tests from North Carolina DOT's there's some results from the approved aggregate list for North Carolina DOT. Since that's where I live, I was looking at these. The average for all sources for the soundness loss test is 0.73%. And then here we have two lightweight aggregate supplies, quarries. They are located on the same source material at different locations, but they have very similar properties. Here you can see that these losses due to soundness are significantly less than the average of the normal weight aggregates, and well below the requirements that NCDOT has for the test loss. Same thing with LA abrasion, where you would think that this porous rock would suffer badly in the LA abrasion test. The average for all rock was 31%, and these two are 31 and 32%. So they're well below the limits that are given for NCDOT. So what I like to recommend is that if you have requirements for normal weight aggregate, the lightweight aggregate should be required to meet those if at all possible, and here it demonstrates that you certainly can. One thing to note is that the test method needs to be adjusted a little bit for using LA abrasion test, because you end up packing the drum with more aggregate than you would have for normal weight aggregate, so it doesn't fall as much. So you should use an equivalent volume, not an equivalent mass. There are several types now as we move on into normal weight concrete, having been talking about aggregate up to this point. We'll begin with some definitions of types of lightweight concrete. Here we have all lightweight concrete. As I already mentioned, that all of the aggregate is lightweight aggregate. Sand lightweight concrete sounds a little backwards, but what it means is that the coarse is lightweight and the normal weight is used for the fines, the sand. And then there's specified density concrete, which is any blend of normal and lightweight aggregates to obtain whatever density that you want to achieve. The all lightweight and sand lightweight definitions were in the specifications up to the 8th edition, where they were dropped, and we now simply specify the density of lightweight concrete, and the supplier determines the blend of the aggregates to achieve it. There are also two types of density that we need to be sure that we use wisely when we specify densities for lightweight concrete. The first is fresh. That's the density of concrete in its plastic state when it comes out of the chute or at the end of the pump line or whatever it may be. And that's used for acceptance at delivery. But we also want to know, well, what's it going to be like a little bit later after it dries out some. Turns out that our mixes oftentimes, because they are higher performance mixes, they don't dry out as much as perhaps a mix that's used for an elevated slab in a building. So we don't have as much change with equilibrium conditions as those other mixes. But at any rate, again, as I read the definition earlier, the density is it's the density of concrete exposed to drying to reach a constant mass. So that's what we're talking about there. The primer discusses different densities that may be achieved, although it can vary with the type of lightweight aggregate used to some degree. The lower the density, the lower the compressive strength that can be achieved. That's even acknowledged in the LRFD for normal weight concrete. But the strength of lightweight tends to be a little bit more sensitive to the change of densities. You can get down into the 95 or 90 pounds a cubic foot range with an all lightweight mix. And also that would include air. We're using air to reduce the density also. And that's how we get to the lowest densities, was with all lightweight. Then we have to add an allowance for increase in density with reinforcement, which is typical for normal weight concrete as well. But what about the hardened mechanical properties? Some tests do show that lightweight has a reduced mechanical property compared with normal weight. But in some cases, lightweight can have properties that are similar to, or even maybe even greater than a comparable normal weight mix. But oftentimes, even if a lightweight concrete property may be reduced, we can modify our designs in some way to deal with that. One thing is, for example, a research test where they keep all the parameters the same and they just swap out the rock. You're going to have a lower strength in lightweight concrete than you do in the normal weight. Not a lot, but you will have some reduction. Well, in production, out in the real world, you would just bump up the cement content a little bit for the lightweight, and you'd end up with the same compressive strength. So that's just something to bear in mind. Looking at lightweight concrete decks, we can typically use the same compressive strength that we use for normal weight decks. That's easy, no problem to achieve for a lightweight deck. In a few cases, people have increased the lightweight concrete strength because they think that we have a reduced tensile strength for lightweight. That's a possibility, but we'll see some data that refutes that later on. For girder concrete, 28-day compressive strength can be used 8 KSI or maybe even up to 10 KSI. And in some cases, this is just a little caution here too. Some researchers have reported that they can't achieve higher strengths with some lightweight aggregates, but sometimes they don't have as good an understanding of how you work with lightweights than some of the suppliers for lightweight aggregate. So I would encourage you all to consult with lightweight suppliers when considering the higher compressive strengths and see what they think about how to achieve that. As far as tensile strengths, modulus of rupture is often used as the indication of tensile strength. But what we find is that instead for lightweight concrete, we typically specify the splitting tensile strength of lightweight concrete. One thing that you do see is we have a concrete density modification factor, the lambda term, that's now finally, well, back in 2015, it was added into the specs. Prior to that, it was simply stated in text prior to the equation, but now the lambda has been added into all the equations where it belongs. So I would encourage, if you're looking at tensile strength, that you would use the splitting tensile strength rather than the modulus of rupture. Here's some example of some data on tensile strength for lightweight concrete. Here we have a normal weight mix that used river gravel, and then we had lightweight mixes that used the 3 different types of lightweight raw materials. This is the splitting tensile strength that was measured, the compressive strength, and then the ratio. Oddly enough, if you look at this, and this is essentially the expected splitting tensile strength for normal weight concrete in the denominator. Of these 4 specimens, the only one that came in under the expected for normal weight was the normal weight concrete. All of the lightweight tensile strengths were higher than would be expected had the normal weight concrete equation been used. So this is where I'm saying that while people think that lightweight always has a reduced tensile strength, it's just that the specifications have allowed or have provided a modification in case they were. And we've just all come to use the 0.75 for all lightweight and 0.85 for normal weight, but that's, for sand lightweight, but that's not really the case. So I would encourage you to look into that and think otherwise if you have opportunities where that might make a difference. As far as compressive strength, the strength gain with time is similar for lightweight, and the stress strain curve is typically linear, a little further up than normal weight, but we haven't really quantified that very much. As far as modulus of elasticity, the lightweight concrete is less stiff than most normal weight concretes. There's an equation in the code that came in 2015 that's better calibrated for higher strengths as well as for lightweight concrete. And we have the unit weight that's in there, as it has been for many years, but in a different equation now. This is an interesting set of data coming from pre-stressed girders up in Washington State, where you're looking at creep on the left and shrinkage on the right. The red lines are for lightweight concrete, the green lines are for normal weight concrete, and you see that in both cases the creep is less than the lightweight creep is less than the normal weight creep, and on the right you have the lightweight concrete is less than the normal weight as far as shrinkage. That's very surprising because the lightweight concrete actually has about almost 25% more cementitious material in it than the normal weight, yet it has a reduced shrinkage. So that's probably due to reduced shrinkage due to reduced autogenous shrinkage due to internal curing. That's probably the main thing that's going on there. But it's very surprising. But it's clearly demonstrated here, and it is repeated with other data. So creep and shrinkage are not greater typically for lightweight concrete than they are for normal weight. A point that we don't often spend time talking about is the coefficient of thermal expansion. Lightweight concrete values are typically less than for normal weight concrete, as you can see here on the chart. This is again deck concrete mixes. As far as design parameters, they are discussed in the primer. One thing that we oftentimes think about with or discuss with lightweight concrete are the pre-stress losses different? Well, what some of the testing has shown is, yes, the elastic shortening is greater because you have a reduced modulus, but there's not a significant difference between the creep and the shrinkage. We just saw that it could even be less for lightweight concrete. So we can use the equations that are in the specifications. Camber will typically be greater because you have less dead load and a lower modulus. So the camber typically can be more. We may be able to mitigate that in our designs if we choose to. But otherwise, we use the requirements in the LRFD specs for our design without any problem. The primer also discusses a number of aspects of durability. You can see them all listed here. Typically, the lightweight concrete can be shown to have comparable durability to normal weight. Won't be able to go into that in further detail. Again, there's some discussion of internal curing. I've already mentioned that. The New York State DOT has a specification now that allows a reduction even in the required duration of wet cure if you have internal curing with lightweight aggregate in the deck concrete. Also, any lightweight concrete that's using the pre-wetted lightweight aggregate will provide internal curing. Here's a great example of how internal curing works. This is a trial placement for a slab on grade. It represents the floor of a large water reservoir. I mean, it's like a 10 million gallon reservoir or something, very large concrete placement. This is just the trial placement. The concrete on the left has internal curing in on it. The concrete on the right does not have internal curing. No conventional curing of any type was applied to either concrete. And this is what they looked like the next morning when they came out and looked at them. So there's not sprayed curing compound or anything on these. Just the internal curing is clearly still moist, while the conventional concrete has dried out at the surface, which makes it more prone to shrinkage cracking and such. Now we're ready to move on to the next 4 chapters in quick succession with just one slide for each. Here we are looking at Chapter 3 on initial design considerations. So we as designers have to have some understanding of, well, what numbers do I use in design? Why would I use lightweight? So you can see the list of what needs to be considered here. I won't go into details. You can look at those in the primer. Chapter 4 is a much more detailed look at the LRFD design specifications, what they say about lightweight concrete. And also, there's a discussion of recently adopted changes related to lightweight. And then there were some, that this isn't discussed in the primer so much, but there are some additional changes that were identified as I was writing this that now have gone back to ASBI, and they've made a change that will be coming out in the 10th edition. There's a chapter on construction considerations with topics related to construction. You can see them all here. There's also a section on internal curing. There's a section or chapter on specifying lightweight concrete, because this is very important. If you're going to build something out of lightweight concrete, we have to specify it, especially since many DOT standard specs don't include all the information or test methods that are required for lightweight concrete. There's not a lot of differences, but there are some things that are important that need to be added. So that is discussed in this chapter. So we finally get to Chapter 7, the project examples, where we have a list of different bridges for which lightweight's been used successfully for 3 different reasons: improved structural efficiency, reduced element weight for shipping and handling, and then allowed reuse of existing structural elements. And I think we're going to cover those in a moment in reverse order. But we do also have a wide range of bridge projects here, large and small, short and span and long spans, new and old, different parts of the bridges, all of its superstructure here pretty much. We don't go into internal curing examples, however, in Chapter 7. So here we start out by looking at what about projects that reuse existing structural elements. There are 2 of them here, the I-5 bridge and the beach bridge. I'll have a slide for each, and the only point I'm really wanting to make here is that lightweight concrete was used here because it kept reanalysis of the piers out of the picture. They kept the weight of the new superstructure small enough that there was no reanalysis, redesign, or retrofit required for the piers, which is a significant issue. The beach bridge was just a short bridge with about 56 and 39 foot spans, 2 spans, but it was in a situation where it would not be easy to replace the piers. So using the lightweight concrete next beams made it work out well, and they could reuse the substructures. There are a couple of other bridges. You see the 5 more here that are for which information is given in the primer, where the existing structural elements were substructures were reused. Here's some where bridge projects had improved structural efficiency because of the use of lightweight concrete. We're not going to discuss San Francisco Oakland Bay Bridge because we've already talked about that, but I'll quickly touch on the other 4 here. The Benicia Martinez Bridge, a major bridge just north of San Francisco, California. It's cast in place box girder, has a total length of 6,500 feet, but a maximum span length of 658 or 201 meters. Lightweight concrete was used for the entire box girder section, except for the pier segments. And the lightweight concrete was used in order to significantly reduce the seismic forces from the mass of the superstructure, which then affected the foundations and therefore the cost. Here's the bridge that I started out mentioning on slide 1, where these bridges used lightweight concrete because of the loads on poor soils. Here's one of the world's longest spans, if not the longest segmental box girder cantilevered construction span. The center span is 988 feet, and then it has the 2 side spans. Lightweight concrete was used out in a section of the main span in order to reduce the weight of the main span to better balance the design with the short side spans. Then here's another bridge that's a little bit different in that it has a cable stayed bridge. This is again in Norway. Cable stayed portion and then a floating bridge portion. Lightweight concrete was used in the main span of the cable stay to reduce the cost of the stays. And lightweight concrete was also used for the pontoons, and it saved a significant amount, reduced the size of the pontoons and things like that. And a couple of other cable-supported bridge structures have also used lightweight concrete. What about projects that reduce the weight for shipping and handling? We see the I-5 bridge here. This is, excuse me, not the I-5, but the Portland Avenue bridge in Tacoma, Washington. This bridge needed to go, so I think it's only about 6 miles from the plant, but in order to be able to ship that, they needed lightweight concrete because the girder is 223 feet long, one piece. And really it's 230 feet long because it has terrible skews on both ends. And so for point to point, it's 230 feet. So lightweight was just used for this to transport the girders to the site. And here's the record span for spliced girder bridges, where the drop-in is lightweight concrete. You can see them on the barge in the bottom photo, and then being erected using strand jacks being picked up 2 at a time on the right photo. And with that, we're at the end. I hope that this presentation's exposed you to some new information about lightweight concrete. It's not a new material. It's been used for over 100 years now. That it has advantages for all types, even parts of concrete bridges, that the design procedures are well developed and it has already been used in a wide variety of bridges, and that information is available to assist regarding construction issues and specification development. The document is posted on the FHWA Concrete Bridges webpage. You see the link here. I encourage you to download the primer. It's also going to be in the chat. The link will be in the chat window also. Reggie Holt is listed here. He's the contact for the primer at FHWA, and he actually just yesterday I was reviewing the article that he had prepared for the summer issue of Aspire magazine. We're going to talk about the primer in that article. And I hope that you're getting Aspire magazine. If not, you ought to check it out. It's a free magazine about concrete bridges. And I thank you very much for your participation and attention. And I've run a little longer than I had hoped. And with that, we will stop and see if we can field a few questions.
Well, thank you, Reid. We appreciate your presentation. And yeah, we have a couple minutes for questions. Little note to the attendees: if you need to leave at the top of the hour for other commitments, that's fine. We're going to go ahead and run maybe just a few minutes after the hour because we do have a couple questions that I would like for Dr. Castrodale to field. Wade Bonzen with FIG Engineering Group, who's also the chair of the ASBI Construction Practices Work Group, is going to be serving as our moderator for the Q&A, and so I'll turn it over to Wade.
All right, very good. Thank you, Greg, and thank you for a great presentation, Reid. That was excellent. We've got a few questions that have been submitted by our attendees today, so we'll start with the first one here. How long does it take for lightweight concrete to reach the equilibrium density? And does the design need to consider heavier density at early stages of construction?
That's an interesting question and a good one. One thing is, if you're talking about a bridge girder that's going to be, or even a precast deck panel or something like that, the concrete's not going to have time to dry out to equilibrium before it's shipped, probably, especially if it's a fast track type thing. So in that case, when you're computing handling loads, you should probably use the fresh density to compute those loads. One thing is with our concretes in the transportation industry, we're looking at low permeability type mixes. Well, that means water can't get in, but it also means it's a lot harder for water to get out. And I think that for most situations, our equilibrium densities may not achieve the amount of drying that we sometimes look at. In fact, I know with Virginia DOT's taking a look, and their preference right now for girder design is to simply specify the fresh density and use that from then on. You might lose 2 or 3 pounds of weight with time, and that's not a significant number compared to 125 pounds or so. So that's discussed in the primer, and I would encourage you to think about that. Feel free to give me a call if you have more questions. The time, because we have slower, we have concretes that have slower release of or movement of water through them, you have to be a little bit careful about even drying the concrete if you did it manually. There was a report by Georgia Tech back a number of years ago where their air dry concrete after a couple of years is actually lower density than their oven dried concrete where they stopped early. They didn't know they were stopping early, but it's just a very slow release of the water. Anyway, that's probably more information than I need to give, but it's typically a pretty slow process to get the water out of the concrete.
Okay, great, thank you. Another question here. Could UHPC be produced using lightweight aggregate? Is that something that could be done, and are you aware of any examples of that?
One feature of UHPC is that it really doesn't use coarse aggregate. It only uses some fine aggregates. So you're not going to get much weight reduction. The fine lightweight aggregate particles are typically heavier than the large lightweight particles. You could use lightweight aggregate in UHPC. You may get some reduction there. I know that there's just a couple of people who have thought about that. But one of the things that may be beneficial for UHPC is that much of the cement or cementitious materials in UHPC does not hydrate because there's not enough water. So if you were to use lightweight aggregate that's pre-wetted, you may be able to hydrate more of that cement that's currently only being used as filler. So I don't know that you're going to get a light UHPC, but you might get a little bit of reduction in weight, but you may also get a little more efficient use of the cementitious materials if lightweight aggregate fines were used in it.
Okay. Another question, have there been examples of lightweight concrete applied to ductile elements like columns? And are there any design guidelines available for those types of elements?
Yes, there are. In fact, on the Benicia-Martinez Bridge, I talked to Juan Murillo, who was one of the designers involved on that project. And UCSD was doing some research at the time they were designing that, looking into the ductility of lightweight concrete. And he said that if that research had been finished prior to or during the design of that bridge, everything above the footings would have been lightweight concrete, because you can get adequate ductility for the columns, and the pier segment would have also been lightweight concrete. So I've always been impressed by him saying that. There's been some other research. I'm not sure that there's anything in the specs about that at this point, but I do give a couple references in the primer to some of those resources regarding the research that was done at UCSD, and then there was some follow-up at North Carolina State.
Great, very interesting. Okay. Another question, is there a difference in the load carrying capacity of a lightweight concrete member, say, compared to an equivalent normal weight concrete member for live loads?
For live loads, not typically. They would be, you could design them to resist the same loads. You're using the same stress blocks. You're using the, for a pre-stressed member, you're going to have essentially the same strands in them. So I think that you can design a lightweight member to function with the same performance as a normal weight member. And typically you have less dead load in it. So sometimes that helps you, that should help you out with reinforcement and with giving you some more live load capacity in the structure.
Okay. All right, another question here. How is the resistance to chloride infiltration comparable between lightweight concrete and normal weight concrete?
Yeah, that's one of those questions that comes up where you say, you've got a whole concrete you're wanting to give me with holes in the aggregates, and you're saying that the infiltration of chlorides is going to be less, or it's going to be acceptable. And it turns out that you can have less permeable concrete with lightweight due to a number of factors. They're discussed in the primer, but oftentimes it has to do with the internal curing and less micro cracking around the aggregate particles. So that can be very useful. In fact, Virginia DOT, for example, has a low cracking specification in their standard specs. And you can either measure your shrinkage to get it below a certain level, and another option is to use shrinkage reducing admixtures. And then the third is just, in that case, you used to have to do testing. I think they're now going to a standard dosage. And the third case was simply to provide lightweight concrete. And there was no testing required because they were confident that you would get what you needed out of that. There's data that I have Coulomb testing data, a table from a Virginia project that's in the primer to demonstrate that they're meeting the requirements for Coulomb tests. So I think that really we should be comfortable. You give a specification, we should be able to make a lightweight concrete mix that would meet it.
Okay, great. Another question, do you know of any projects that have paired up GFRP rebar with the use of lightweight concrete to further reduce weight? And do you see if are there any foreseeable issues there with the mechanical bond that you need to achieve there with the GFRP rebar?
Good question. I am not sure about any projects that have used lightweight concrete. I know there's been some research done to look at using lightweight concrete with GFRP. I don't think that there should be any significant issue between the two. You know, the specs do provide an increase factor for development length, assuming a reduced tensile strength. But that may not be needed if you don't have a reduced tensile strength. So I don't think I have a good answer for that, but I don't think that there's a good reason to be concerned that we don't have enough, or that we would have a different situation with lightweight than with normal weight. And we do have provisions in the specifications that address development length and that sort of thing. I'm not sure if the GFRP specs include a factor for lightweight concrete or not. They used to say you can't use GFRP with lightweight, but that was only because they didn't have any data on
it. Okay. All right, great, thank you. Could you summarize one more time the difference in modulus of elasticity between normal weight concrete and lightweight concrete?
Sure. The modulus is reduced, and it's going to differ possibly depending on aggregate type, but there's the equation gives a reasonable fit. I mean, the normal weight equation doesn't work either, but it's a plus or minus, I don't know, 20 or 30%. And we're probably within that range with the lightweight concrete regarding that. But what happens is you simply have a porous aggregate. So the aggregate is not as stiff as a solid piece of aggregate. So therefore, you're going to have a reduced modulus of elasticity in the concrete. And actually, that can be helpful in a number of situations, especially like deck cracking, for example, restrained shrinkage, or even mass concrete. Mass concrete, where you have restrained shrinkage there, just due to the mass of it, if you have lower modulus and a lower coefficient of thermal expansion, even though you may have a little bit higher temperatures because lightweight aggregates insulating, you should be able to tolerate greater temperature differentials in lightweight concrete than you can in normal weight concrete. That was for free. You didn't ask that question, so.
Great.
I might make one more little caveat back on another one. People have tended in the past to over-specify lightweight concrete. They start saying, oh, well, we need to make sure that the modulus is this and that, and where they don't do that with normal weight concrete. So you want to be a little careful that you don't tighten down the screws on the lightweight concrete more than is necessary. Just a quick comment there.
Well, thank you, Reid.
Yep. Sorry, go ahead.
Yeah, that's great. I think we're about 10 minutes after the hour, so we probably, I think we've gone through most of the questions. There might have been a couple more. There is in the chat, if you've found the chat dialog box, I did drop a link to the primer that Dr. Castrodale has been covering today. You'll also find his email address if you're interested in contacting Reid for more information after you'd had an opportunity to look at the primer. And I will also then put in a link to Aspire Bridge magazine, which hopefully everyone here is already subscribed to, but there's a link there if you want to click that, and you can do a free subscription, both either electronic or even print, if you're still old school like some of us are. So with that, Wade, did you have anything else?
Nope, I think we've covered it. Thank you.
All right. Well, thank you again, Reid. We appreciate you today for attending or presenting at our webinar today. Again, to the attendees, you should get a certificate of attendance no more than a week from today. So just wait to see those. And then you'll also get a notice when we have posted a link to the recording to this session if you want to go back and visit it again, and also a PDF copy of the slides again if you want to reference those again. Or if you have a colleague who missed today's session, there's certainly opportunity for them to see this session in its entirety. So again, thank you. Apologies for running a little bit long today, but we had some really great discussion and questions. So with that, we'll sign off. So thank you, everybody.
Thank you all.